Okay, so we learned how to calculate the deviation of epsilon, and that is called as the standard error of the regression. And we find that number here, right? That is, this is the standard deviation of the error term. And then, based on that, we can calculate the standard deviation of the estimator, right? So actually, the accuracy of beta estimator depends on the standard deviation of the error term. So in particular, the formula goes like this. So this part, standard deviation of epsilon, this is what we just calculated. This is the standard error of the regression. And uh, like if you think about this, x bar is an estimator for the mean, and then it looked like this, standard deviation divided by square root of n, and then this much is similar to this. We use n minus 1 in the denominator because there is another parameter, beta 0. So you have to keep like one of the observations, one information for the other parameter. So you lose one information when you estimate the other parameter at the same time. So you take n minus 1 in the denominator. And another interesting thing here is you have to divide it by standard deviation of x, right? So that is because beta 1 is multiplied to x, right? So let's see here. So beta 1 is multiplied to x. So you have to adjust the standard deviation of x when you calculate the standard deviation of beta, right? So as a result, you get additional term here. So then they are these numbers. These numbers are calculated based on what you just saw. So you don't need to memorize the formula at all. Anyhow, you are going to just see those, like use Excel to calculate those numbers. But the reason why I'm showing you the formulas is because um, first, I just wanted to show you the theory you learned earlier is applicable to other models. And second, when you learn the variations of the regression model, sometimes you need to think about the formula more carefully, right? So later, yeah, like if you take advanced courses, you may need to start from these formulas. Then you can just like review what I just told you, and it will help you in that case. Okay, so we learned these numbers, and basically, actually, these two columns are the most important uh, estimation results among these outputs. So we are going to use those numbers, and we will see what kind of things we can do, like statistically, with those numbers, like those coefficient estimators and the standard errors. Um, you know, like in our estimation and hypothesis testing chapters, everything was approximated to normal distribution. Here, we do the same thing. The sampling distribution of your estimator beta 1 hat, the estimate is also approximately normal, right? So the mean of the normal has two parameters, mean and variance, and the mean is the true mean, true beta 1, which is unknown. I don't know what is the true marginal cost, but that is the center of the sampling distribution. And the variance part follows the standard error squared. So this standard error gives you what would be the variance of the sampling distribution. So if you take square of this standard error, okay? So this is standard deviation of the estimator is calculated. So you can utilize the normal approximation to confidence interval and hypothesis testing, okay? Right? And confidence interval is pretty straightforward. If you remember the original formula, point estimator plus minus z alpha over 2 times standard error of the estimator. So the reason why we have S over square root n is because this is the standard error of this estimator. Okay, standard error of the estimator takes this form, so we use that here. Now the point estimator is beta 1 hat. The point estimator is this number, 2.383, and the standard error is 0.206. So 2.3 something here, point estimator, and standard error calculated, given in the table here, and you obtain z alpha over 2 from normal table, right? Or from the slide, same table we use. Then that is the confidence interval, okay? Given the confidence level of 1 minus alpha. Then we get these numbers, okay? These numbers are the 95% confidence interval, right? So beta 0, the fixed cost is somewhere in between 5.57 up to 10.8. I don't know where it is, but with 95%, it's somewhere in between them. And the marginal cost is between 1.9 and up to 2.8 with 95% confidence level, right? So if you prefer the interval estimation, you may use that. In case if you want to use different confidence level, you can set up, okay, go to data and data analysis back here. If you choose regression, and you may change confidence level to something else, like say, let's try 99%. If you try 99%, then the 99% confidence interval is calculated here. Okay? So if you wanted another confidence level other than 95%, you can change that. You can specify the confidence level you want in the option. Okay? But usually 95% is our standard, and when you say confidence interval without specifying confidence level, then you have to use these numbers. That's the standard. Okay. Anyhow, these numbers are based on the point estimator plus minus 1.96 times the standard error. Okay, that's how we obtain those numbers. And now let's go to the hypothesis testing. In the regression model, the most important hypothesis we have to be concerned is this. So if the marginal cost or the slope of the x variable is 0, that means then our regression model is pointless, right? So the goal of our regression model is to explain y using x. We use information in x to explain y. But if they are not related to each other, then the regression model is useless, right? We cannot predict y based on x. X does not help predicting y. So that is, if the slope is 0, effect of x on y is 0. So when x changes, y does not change. That means x does not help. X is useless in predicting y. So your regression model is useless, right? So we have to be worried about that problem. So what I'm going to do is we are going to assume that x is useless, but we hope to reject that hypothesis. And if this hypothesis is rejected, that means x is statistically very significant, like statistically very helpful. There is a strong evidence that x changes y. So your regression model is helpful. Okay, so remember that. In the end, we'd like to reject it. We'd like to reject the null hypothesis, because the null hypothesis means your x variable is useless, right? And then the process is the same. We are going to calculate the t-statistic like this. But remember, the t-statistic was calculated this way. X bar is your point estimator calculated from the data. mu0 is the value in your hypothesis, null hypothesis. And you standardize the difference by the standard error. Okay, that was the formula. Now we are following the same thing. Beta 1 hat is the point estimator calculated from the data. Minus, you have to subtract the value you assume in your hypothesis, but that's anyhow 0. So you are going to subtract 0, which disappears, and standardize the difference by the standard error of the estimator, standard deviation of the estimator. Okay, so this is the t-statistic, which means the standardized difference between your data and your hypothesis, standardized by the standard error. And then based on the t-statistic, you are going to calculate the p-value, which follows exactly the same formula because everything is approximated to the standard normal distribution. So this t-statistic is approximated to the standard normal distribution. So p-value is the same. The idea is we are going to calculate the probability outside your observation. So the probability that you observe more unlikely outcomes. Okay, they are calculated here, t-stat and p-value. Going back to t-stat and p-value, these numbers, t-statistic is calculated like so. So this t-statistic 6.98 is the standardized difference between the fixed cost estimate from zero, right? And 11 is the standardized difference between the estimated marginal cost from 0, right? So, and those numbers, t-statistics, are extremely, like the p-values are very close to 0, right? You have to have a lot of zeros, 0.004%. That is the p-value. And remember, just a review, in this case, given those numbers, do you reject the null hypothesis that the marginal cost is 0 or not? It is two-tail test and at 1% significance level. So at 1% significance level, can you reject the null hypothesis that your regression model is useless? So remember, the significance level 1% means you are going to reject top 1% suspicious models, right? So in this case, your p-value is 0%. That means it is one of the most suspicious result. But in this case, suspicious is a good thing because, like, you can interpret. Let me interpret this. So you are going because you are going to reject the null hypothesis because, right? I said you are going to reject top 1%, but you are top 0.0000 like percent, very very suspicious. So you are going to reject the null hypothesis, which means your model is not useless. Your model is meaningful. Then let me explain it this way. So that probability is calculated like this. Suppose that the marginal cost is 0. If the true marginal cost was 0, still you may get this estimator. Your data could have random errors, so your estimator is very wrong, and as a result, it is estimated to be 2.3, even though the truth was 0. But only because of the random error, you may get 2.3 estimator, right? Estimator 2.3. But for that to happen, it's really, really unlikely. That kind of error, the error is as huge as 11. So that much error is really rare. It does not happen. It's not even like 1%. It's less than 0%, right? Or like that kind of error can happen with 0%. So it's unlikely to happen. That much error does not happen that much. So you have to reject. You have to reject the null hypothesis. So in the end, you are good. You're happy to reject the null hypothesis because the null hypothesis means your model is useless. X has no effect on Y. Okay. And this is what you wanted. And then when you reject the null hypothesis, we say that beta is statistically significant, right? P-value is smaller than the null, like the significance level, so your null hypothesis is rejected. So when you reject it, your estimator is statistically significant. In other words, statistically different from zero, which is good thing, which is what you want. So actually, now we learn hypothesis testing first, and then we learn regression later. But in the history of statistics, regression model was developed earlier, and the statistical significance was used for regression coefficients first, before hypothesis testing framework is developed. So actually the significance, the word significance is originated from regression literature. Okay. So far we learned, we considered pretty simple model. Now let's move to more realistic data work. Real data. We have data on wage, hourly wage, and years of education. I am curious how much, what is the returns to the education? If you attend school one more year, then how much your wage will grow, right? So beta 1, especially in this regression model, X is education, Y is your salary, your wage, and beta 1 is the returns to education we are interested in, right? And then how can we interpret beta 0? It is the fixed cost. That means beta 0 is the expected wage even if you have zero education, right? In our example, because in our data, in reality, there is no one who get zero education. It's almost does not exist, such a person. Zero education does not exist, so beta 0 itself has no direct implication. Let me explain that later. We'll come back to the case later. And I have data on education and wage on more than 2,000 people, like nearly 2,200, 44 people. I have data. And education, 12 years of education means high school graduation, right? And 16 years means 4-year college graduation, okay? 14 years means like 2-year college graduation, and like 17 years means 1-year master program, 18 years, 2 years master program, and like 15 years means like college dropout, something like that, right? So 11 years means like he or she completed 11th grade, but did not complete a high school degree. So 6 years means like elementary school graduation, things like that. Also, you have wages. So you can just open it and let me see. Wage distribution, like the smallest, the minimum in our observation is $1 per hour. And it goes down to $40. Some people earn like more than $40 per hour, but some people earn $1, right? So we are going to run a regression model using these two data. So again, go to regression, and I will take off, like say, Y variable, the output is salary or wage in our data, and X variable is education. Okay, I'll choose the whole column, and I will click OK. Oop, what? So maybe it doesn't work. I'm sorry. So Y range must choose the data only, not the whole column. And X range also this column only from number 1 through row number 1 through row 2245. Okay, if you click OK, then you get this plot, right? So the plot is not that beautiful because the horizontal axis is integers, right? So interestingly, there is a person who has zero education. I think this is an error. So maybe this person wanted to say meant 10, but somehow mistyped it and entered 0. I think anyhow, we have to admit, acknowledge those errors. Error can happen. I don't know what happened to this guy. Error happened. And 4, 5, 6 up to 18, right? 18 is the highest education in our observation. And surprisingly, and interestingly, there are a lot of people, rich people, who make $40 an hour throughout wide range of education. Even if this guy have did not finish say high school at all, 9 years, completed only ninth grade, still one of the richest, right, making the most money. And there are some people who completed 18 years, but who's making one of the minimum wage, right? Anyhow, this is the distribution across education. But we are going to make a straight line going through those dots, scatter plots. So to make it better, I'm going to use change it to marker option none. So what happened? So we have a line like this, which is predicted wage, hourly wage, but the blues are real observations. Real observations do not show the pattern clearly, but by the regression model, you can clearly tell what is going on. So it is natural that your wage increases as you get more educated. Okay, back to slide. So that is real data analysis from National Longitudinal Survey in 1997. Okay, so a long time ago. Data is a long time ago. So then, based on the data, okay, back to the analysis, we are interested in these numbers first. So our estimate, especially, we are interested in this number. This number tells you that when you get 1 year education, your hourly wage increases by $0.74. That's the estimation result. And its standard error is 0.045. So these two are our main estimation results. Okay? Based on these numbers, you try to calculate the 95% confidence interval for beta 1. Okay, I will finish this video here. You try this question after this video, and I'll come back and give you the answer to this question. Okay, see you later. Bye.